Okay, so let's work a couple of examples covering sugars, just reinforcing some of the concepts that we talked about in today's lecture. So the first example is from last semester's exam, where I asked the students to provide the full name of the sugar idose shown below. So this is the Haworth of the sugar idose, and remember the nomenclature is the anomer form, followed by the stereochemistry, DRL, followed by the name of the sugar, including the ring size. So here we look, the anomer is actually the beta anomer because the OH group and the CH2OH moiety are on the same side, so we have the beta anomer. Because the CH2OH group is pointing down, we know that this is the left enantiomer. And we know the name of the sugar is idose, so we go ido. We have a 6-membered ring sugar, idopyranose. So that's how you would answer the question. All right, for the second question, it's asking us to draw the Haworth projection for L-fructose. Remember, L-fructose is one of the Fisher projections you need to know. It's specifically asking for the furanose form. Here are the kind of examples of the furanose and pyranose ring structures you'll be given on your exam. Remember to only ask what's being, or answer the question, and so only use the sugar skeleton that's being asked of you. So we're asked about the furanose sugar in this question. All right, so we need to have our nucleophile end in number 5. So we have 1, 2, 3, 4, 5. Okay, so our nucleophile will be this hydroxide group. It'll attack our electrophile, our anomeric carbon. We don't know whether COH, we do know because we kind of know the rules based off of CH2OH. The L is actually going to point down. Okay, so if we want to have the beta anomer, we'll also have the resulting OH group point down as well. This CH2OH group is actually carbon number 1. The anomeric carbon is carbon number 2. Carbon number 3 here has the OH group pointing down. Carbon number 4 has the OH group pointing up. And carbon number 5 had our OH group become, this is the old nucleophile. Our CH2OH group is here from carbon number 5 and our resulting H group. Okay, that's kind of a tricky one. Let's draw the Haworth projection of the alpha anomer of D-ribulose in the furanose form. Again, we're drawing a 5-membered ring. 1, 2, 3, 4, 5. So our nucleophile is going to be here. We're going to attack at the carbon 1 position. I'm sorry, yeah, it's actually C2, our anomeric carbon. Okay, we want the alpha anomer, all right? And now we don't have a terminal CH2OH group because our CH2OH group is actually contains our nucleophile, which will be here, right? So now we must look at the next stereogenic center, carbon 1, 2, 3, 4. 1, 2, 3, 4. This is the next stereogenic carbon center that's going to dictate alpha versus beta. All right, so the OH group is to the right, so it's going to be D. We want it to be alpha, so our OH group is going to be oppositely charged, so it'll go up. Remember, this is from our ketone that's formed when we make a hemiketal. Okay, a ketone and an alcohol reacting. Carbon 1 is CH2OH. Carbon 2 is our anomeric carbon. Carbon 3 here has the OH group to the right, so it's also pointing down. Carbon 4 we addressed, and then carbon 5 will have the two H groups present because our OH group became our O in our furan ring. All right, another kind of tricky one. Now let's go backwards and draw the Fischer projection of the Haworth sugar shown below. All right, so the same types of steps. The first thing you probably want to do is count the total number of carbons, so you can make your backbone of your Fischer projection. Then you want to determine whether you have an aldose or ketose. Determine D versus L stereochemistry. Then fill in your R groups. Okay, so we're looking here, they're labeled, they're nice. 1, 2, 3, 4, 5, 6 carbons. So we'll go ahead and draw out our 6 carbon backbone. Determine whether you're working with an aldose or a ketose. Remember, if your anomeric carbon is carbon 1, it's an aldose, it came from an aldose. If it's any other number, so carbon greater than 1, it originated from a ketose. So here, our anomeric carbon is located there, and so our anomeric carbon arose from an aldose. We know we have a D sugar because our CH2 group is pointing up. And so we originated from a D group. Now we can fill in our the rest of our moieties. So carbon 2 is here, it's pointing down, so that originated from the right. Carbon 3, it's pointing up, the OH group is to the left, and carbon 4, it's pointing down, and so it originated from the right. So your Fischer projection for the Haworth projection should look like this. And this is actually the structure of beta D glucopyranose. Okay. It's not a pyranose, so the actual Fischer projection, that's for the ring structure, would be beta D glucose. Sorry, just D glucose. There's no beta because it's not a ring. So D glucose. Okay? All right, let's draw now the Haworth. Let's go back and draw the Haworth projection for this beta L xylofuranose in the space provided. Again, I didn't copy it here, but you'll get those skeleton drawings where you have a furanose and a pyranose. Make sure you select the furanose. So 1, 2, 3, 4, 5. Our nucleophile is here. We're going to attack our carbonyl. So we are not going to have a CH2OH group. It's just going to have our OH groups. And so our stereochemistry will come from carbon number 1, 2, 3, 4. Carbon number 4, where it's pointing to the left, so it'll actually point up. If it's pointing up, then my OH group on my anomeric carbon must also point up. And so we have 1, 2, carbon 3 is pointing to the, or is to the right, so it's going to point down. And then 4, so it'll look like this. Okay? Okay, then draw the Fischer projection of the sugar below. Again, we want to number our carbons first. 1, 2, 3, 4, 5. Don't forget this is a carbon. Make your backbone. Your fifth carbon is CH2OH group. Your anomeric carbon is an aldose, so you're starting from an aldehyde. Carbon 2 is bottom, so it's to the right. Carbon 3 is pointing up, so it's to the left. And carbon 4, we need to know whether it's D or L. We have the CH2OH group pointing down, so we know that the OH group originated from the left. All right, I think this is the last one. We want to draw the Fisher projection of the sugar below. Now you need to count, all right? And it's hard for students to visualize whether this is the anomeric carbon or whether this is the anomeric carbon or whether this is the anomeric carbon, all right? And this is difficult when you have a ketone. The anomeric carbon must always contain an OH group moiety, always, because remember, this is coming from the carbonyl when you had that hemiacetal reaction. So the first thing we want to do is determine the number of carbons. 1, 2, 3, 4, 5, 6. Draw our backbone. All right, now we want to determine whether we have a ketose or an aldose. Our anomeric carbon is now carbon number 2, and so we have a ketose. All right, then we can look at carbon 3 here. OH group is pointed up, it's from the left. 4 is pointed down, it's to the right. 5 contains CH2OH. The CH2OH is pointing up, so we know that the isomer is D, and so the final OH group was pointing to the right originally. Okay, I'll post the PowerPoint video, but I'll also post the slides by themselves so that you can work these examples yourself. All right, let me know if you have any questions or see any errors. Thank you. Bye.